Hello, everyone. Today we're going to be talking about general linear models. Now, in general, a model is simply a representation of objects and their relationships in the real world. A statistical model, then, is a mathematical representation between a response variable and one or more predictor variables. Now, when we're talking about general linear models, what we're talking about are statistical models that generalize our basic linear regression approach to consider multiple explanatory variables. And these explanatory variables could be either continuous, as in the case of regression, or categorical, as in the case of ANOVA. So for a general linear model, then, we have a single numerical response variable and one or more explanatory variables that can either be numerical or categorical. So probably the simplest general linear model then is a simple linear regression like we've already talked about. So here I'm simply showing a regression between the abundance of spruce cones available to red squirrels and the date in the spring on which the females give birth. And you can see that there's a negative relationship. In years when there's more food, squirrels breed earlier in the spring. And we can represent this relationship using a linear equation where the regression model indicates that the spring breeding date is equal to 146.4 minus 10.6 times the abundance of cones. So 146.4 is our intercept and negative 10.6 is our regression slope from this relationship here. Now we can generalize this a little bit instead of just talking about fitted values to refer to each particular observation I. So we can describe each individual observation in this regression using this equation where the difference between each observation and the predicted value from this line with this intercept and this slope is equal to the residual for that particular observation. So here we can describe all of the observations in our data set using our linear regression and considering the residuals or the deviations of each observation from this regression. And we can generalize this notation of a linear regression like this, where we have observation I for our response variable y being equal to our intercept denoted by beta naught plus our slope beta 1 times the x or predictor value for observation I plus the residual for observation I. Now this is the situation for a simple linear regression. And we can generalize this in a general linear model by considering more than one explanatory variable. So here I've simply replaced beta naught with alpha. These both are alternative ways of referring to the intercept. But now we have two predictor variables, x1 and x2. And here we're indicating their interaction, the interaction between x1 and x2. So now here we have a general linear model that's a little bit more complex, where instead of having a single predictor, now we have two predictors, x1 and x2, as well as their interaction. Now note we still have this error term at the end, which represents the residuals, where we assume that these residuals are normally distributed with a mean of 0 and some constant variance sigma squared. Now we can also write out this general linear model without referring specifically to the slopes and simply indicate that the response is equal to some constant or the intercept plus the effect of variable 1, the effect of variable 2, and the interaction between variable 1 and variable 2. So we can take the simple linear regression that we did before and make it a little bit more complicated and consider both the effects of cone abundance and the effects of age on the timing of spring breeding. And what we can see then is that in this more complicated model with two predictors, we have spring breeding date being equal to 156 minus 10.8 times the cone abundance that that individual experienced minus 2.9 times its age. So the more food we have, the earlier in the spring the squirrels breed, and the older the squirrels are, the earlier in the spring that they breed. So now we're starting to put together a little bit of a more complicated general linear model that in this case has two continuous predictors, cone abundance and age. In addition to continuous predictors, general linear models can also have categorical predictors, and this is equivalent to our ANOVA scenario. Here we again have the timing of spring breeding by squirrels, but the predictor that we have in this case is not a continuous predictor, but a categorical predictor, where we're treating each year as its own category. And we can model then the observation for each individual I within year J as being equal to the overall mean plus the effect of being in year J plus the residuals for individual I in year J. And so just like with our continuous predictor, we can describe each observation as the sum of these various effects plus some remaining unexplained variation as the residual. General linear models allow us to combine both categorical and continuous predictors in whatever ways we like. Now, one of the simpler ways that we might do this is using what's called an ANCOVA, or an analysis of covariance, which is a cookie cutter type of analysis that typically involves a single categorical predictor that we're interested in. Say, in this case, the differences in the timing of spring breeding between yearlings and older females, while controlling for some continuous covariate that is oftentimes a nuisance variable that we simply want to control for in order to test for our treatment or categorical effects. But in some cases, the continuous variable is also of interest to us. So again, just like before, we can write out our linear model where the observation for individual I in group J, referring to either yearlings or older females, is equal to the overall mean breeding date plus the effect of being either a yearling or an older female, plus the slope or influence of cone abundance on the timing of spring breeding, plus this residual term or the unexplained variation. So you can see then that general linear models represent this umbrella framework that encompasses many of the models or analyses that we've already talked about in the course. So a linear regression, a multiple regression, a one-way ANOVA, a two-way ANOVA, an ANCOVA, all of these are special cases of a general linear model. In each case, we can write out our response variable as being the sum of different effects, whether those effects are from continuous predictors or categorical predictors. When we have only a single continuous predictor, we call this type of general linear model a linear regression. When we have multiple continuous predictors, we refer to that as a multiple regression. When we have only a single categorical predictor, we call this a one-way ANOVA, or in the case where this single categorical predictor has only two levels, we call it a t-test. When we have two categorical predictors, we call this a two-way ANOVA. And when we have a categorical and a continuous predictor, we call that an ANCOVA. But all of these are just special cases of a general linear model. And for the most part, we can leave all of these special other names aside and simply think about general linear models, which provides us with a really flexible modeling framework to allow us to incorporate any number of continuous or categorical predictors in our attempt to try and explain variation in some response variable. The nice thing about this common framework is that in our statistical package R, we can use a very consistent notation for specifying our model, regardless of whether we're talking about categorical or continuous predictors. So all three of these are general linear models that we've talked about already in this video. In the first case, we've got a simple linear regression where we're predicting the Julian date on which females bred by the availability of food. And we use the linear model or LM command in R to specify that this is a general linear model. And you can notice that we use the exact same notation, Julian date modeled by age, whether this is a categorical or a continuous predictor, or any combination of the two. So we can use this general modeling framework and this consistent modeling syntax in R to refer to all sorts of different types of general linear models. So general linear models then represent a unified framework that provides us with a lot of flexibility to analyze different sorts of situations using this same overall framework, which encompasses all of the techniques that we've talked about so far, including regression, t-tests, ANOVAs, and ANCOVAs. Now, if you recall, the reason we were performing regressions was because we were interested in coming up with this regression equation that we could use to make some predictions. So we've already gone over what this regression equation is. So for example, we could predict what the breeding date of a female is likely to be for a cone abundance equal to 4 by simply substituting a cone abundance of 4 into our equation and calculating that the fitted value, or the predicted date on which we expect females to breed in the spring when they experience a cone abundance of 4, is equal to 104, which as a Julian date corresponds to April 13th. And we can also do the same thing for discrete variables, but the calculations are perhaps not quite as intuitive. We're going to start with discrete or categorical variables that have only 2 levels. So in this case, we're essentially talking about a t-test, comparing the spring breeding date of yearlings to older females. But we can represent this t-test as a general linear model, where we're modeling the breeding date of individual females as being equal to some intercept plus some effect of being in category J. Now, it's a little bit weird to be thinking about a slope and an intercept when we're talking about categorical predictors, but our interpretation of the intercept and the slope are still the same. What's different is how we describe this effect of age. In this case, age is a category with 2 levels. So what we can do is to code age as representing whether or not a particular observation is for an older female or whether it's in fact for a yearling. So we can think of this age predictor as being a question that we have either a yes or a no answer to, where yes is coded as a 1 and no is coded as a 0. So for example, we might predict the breeding date of a female, and if she is in fact an older female as opposed to a yearling, we would insert the value of 1 for this categorical predictor age. So if this is the result of this statistical model, we have an intercept of 124.3 and a beta of the effect of age of -6.9. And so what this means is that the effect of being an older female is to advance the timing of breeding by 6.9 days beyond what we would expect if the female was not an older female, which is represented by our intercept. So let's walk through that. Here we have our regression equation then, where breeding date is equal to 124.3 minus 6.9 times the age category, which we interpret to be a question: is the female older? So in the case of predicting the breeding date for a yearling female, the answer to the question of is the female older is no. So in this case, we insert a 0 in place of this age categorization, and this term drops out, and our predicted breeding date for yearlings then is 124.3. If we want to calculate the predicted breeding date of an older female, the answer to our question, is the female in the older female category? The answer to that in this case is yes. So we insert a 1 here, and we calculate the predicted value for older females then as 124.3 minus 6.9, which is equal to 117.4. So here, all we've done then is to use a general linear model as a bit of a weird way of calculating the mean breeding date for yearlings and the mean breeding date for older females. But the way that we've represented that is as the intercept, or the value of the y variable when the x variable is 0, and the effect of being an older female relative to a yearling female, which is to breed 6.9 days earlier. So what our beta, or our slope, represents in this case of a categorical predictor is the effect of being an older female relative to a yearling. And when our categorization, or our answer to this question, are you an older female, is no, and we insert a 0 for this age category, then what we recover is our intercept, which is the average breeding date of yearlings. So we have the average breeding date of yearlings and the effect of being an older female relative to the breeding date of a yearling. So here we've described how we can interpret this slope estimate when it refers to a categorical predictor. This represents the effect of being in this category relative to the category represented by the intercept. So here we've gone over how we can use a general linear model to assess the effects of a categorical variable on a continuous response. Now, in this case, we were dealing with the simplest possible categorical variable that has only 2 levels. But if you have this basic idea of how we can code categorical variables as being a series of yes/no questions, are you in this category or not, where our slope represents the effect of being in that category relative to some other reference category, then you're golden. Then you're well on your way to being able to understand how we might interpret a more complicated model that has more than 2 levels in a categorical predictor. In order to understand how we can expand this basic idea to more than 2 levels within a categorical predictor, we need to understand that we can still use these series of yes/no questions represented by the binary categorizations of 0 for no and 1 for yes, and that we can represent k categories by k-1 binary questions. So in this slightly more complicated example, where we have 4 different levels that we want to assess the effect of these 4 different years on spring breeding date, then we can categorize these 4 different levels by 3 separate yes or no questions that can define these 4 different levels. So for example, we can ask, is a particular observation from 2001? Is the observation from 2002? And is the observation from 2003? Now, obviously, if the observation is from 2001, then the answer to this question is yes, and we would insert a 1 as this categorical predictor. But because an observation can't be from 2001 and 2002, then necessarily we would insert a 0 here and a 0 here. Okay. Now, what about the case when the observation is from the year 2000? In this particular case, the answer to our question, is it in 2001, is no. So we insert a 0 here. Is the answer to the question, is it in 2002? No. Then we insert a 0 here. Is it in 2003? No, we insert a 0 here. And so all of these terms drop out. And we can see that these 3 yes or no questions can also appropriately categorize 2000, because if we answer no to all 3 of these questions, then we know that the observation must have come from the year 2000. We can also tell then that in this linear model notation, that what our intercept represents is the average breeding date for the year 2000. Because if we answer no to all of these questions, then we know that the intercept must be equal to the year 2000, because our definition of the intercept is the value of y when all of our x values are equal to 0. So when the answer to the question, is it from 2001, is 0? Is it from 2002? No, so that's a 0. Is it from 2003? No, so that's a 0 as well. So when the observation comes from the year 2000, the answer to all of these questions is no. And as a result, the average breeding date for the year 2000 is represented by alpha, or our intercept. So in this particular linear model then, when we run the model, we get a slope estimate for each of these effects corresponding to numbers like 5.8, 5.6, and 5.1. So the average breeding date in the year 2000 is equal to 120.1. So the effect of breeding in the year 2001 relative to breeding in the year 2000 is that you breed 5.8 days later. And you breed 5.1 days later in 2003 than you would in the year 2000. So once again, when we want to calculate a predicted value for a particular year, we simply need to answer these questions. Is the observation from 2001? If it is, we insert a 1 here as our categorical predictor, and zeros in each of these other places, because the observation was not from 2002 and it was not from 2003. And doing this same procedure then, we can calculate predicted values or describe each observation in this data set by its breeding date, this linear model, and then the residual term at the end. So in order to analyze the effect of discrete or categorical variables, your statistical package needs to recode these categorical data. You don't need to do any recoding. You can simply specify the years or specify the species or the other categorical variable that you're dealing with. But in the background, the statistical package needs to come up with what's referred to as a contrast matrix, or a series of yes or no questions that help to differentiate all of these different categories from one another. So you don't need to do this coding yourself, these series of zeros and ones on your own, but you do need to understand how your statistics package is doing that if you want to be able to interpret the parameters that you're getting out the other side. And this is because there are many different ways that you can describe the differences among these different categories, and each statistical package has its own technique or preferred way of generating this contrast matrix. Now, the particular contrast matrix or coding system that your statistical package uses isn't going to affect the significance of your categorical predictor, but it is going to influence the interpretation of what those parameters or slope values mean. So let's work through a hypothetical example, where as a dependent variable, we have the number of offspring produced, and as predictors, we have a continuous predictor of body size measured in grams. We have a categorical predictor with 2 levels, either male or female. And we have a categorical predictor of breeding status with 3 different levels: juvenile, first year, or repeat breeder. So you might set up your data in a spreadsheet looking something like this, where we have our continuous predictor of mass, our categorical predictor of sex that's coded as either an M for male or an F for female, and our categorical predictor of breeding status, either juvenile, first year, or repeat breeder. Now, this is how you might set up your data file in your analysis. But what happens in the background that you don't see is that your statistical package is going to represent these different levels in your categorical predictors by a series of yes or no questions, where yes as an answer is represented by the number 1 and no is represented by the number 0. So if we replace this sex variable with a question, is the sex equal to male? Then we replace the M with the number 1 representing yes, and the number zeros representing no, in this case for females. Now, our breeding status categorical predictor has 3 different levels: juvenile, first year, and repeat breeder. And if you recall, we can completely describe a categorical predictor with 3 different levels using 2 different yes or no questions. First of all, is the breeder a first-year breeder? Is the breeder a repeat breeder? And if our answer to both of these questions is no, then we know that it must be a juvenile. So this coding of 0, 0 represents a juvenile, 1, 0 represents a first-year breeder, 0, 1 represents a repeat breeder. So in this case, we've represented K levels in our categorical predictor by K minus 1 yes/no questions about which level each observation corresponds to. So this coding that I'm referring to is the process by which your statistical package will convert a categorical predictor into a series of yes or no questions, the answers to which are represented by ones and zeros. Now, as I mentioned, we need K minus 1 yes or no questions to completely describe a categorical predictor with K different levels. Now, the particular way that your statistical package generates this contrast matrix or series of ones and zeros representing which particular observation goes in which category will depend on the particular statistics package you use. And in some cases, you have some control over what particular contrast matrix you want your statistical package to use. Okay. One of these contrast matrices is referred to as the treatment contrasts in R. In a treatment contrast matrix, the first category, or our control category, is omitted from our yes or no questions. And so this is the category that's represented by the intercept. And each of the other parameters then represent the effect of being in some other category relative to being in the control category or the first level in our categorical predictor. And this is the default contrast matrix that R uses. But there are other contrast matrices that you can use. You can use something called a treatment means contrast, which removes the intercept, or something called the Helmert contrast, which is the default in S+. Now, things like the Helmert contrasts are much more complex contrast matrices that we're not going to get into here, but it is important to know what contrast matrix your statistical package is using so you can know what those parameters mean when you're looking at the results of your statistical model. So once we've generated this contrast matrix, then how do we go about calculating the various parameters that come from our statistical model? Well, the first thing we need to do is to add a constant of 1 to our matrix. And we can then use some matrix algebra to say that our vector of response observations is equal to this matrix of predictors, including our constant and our coded categorical variables, multiplied by this vector of parameters, including an intercept and an effect of each of the different predictors, whether they be categorical or continuous. So in matrix notation, then, this vector y is equal to this matrix X, defining all of the relationships of our predictors, multiplied by a vector of parameters called beta, plus our unexplained variation epsilon. And so we can use matrix algebra then to solve for these parameters beta using least squared methods. And that is, we can ask the question, what set of parameters minimizes the squared deviations between our observed values and our fitted values? In terms of crunching the numbers, what happens is that we take our linear algebra equation and we rearrange it, and we take the square of both sides, and we then take the derivative of this equation, set it to 0, and solve for the parameters in beta. So we're trying to minimize these squared deviations with respect to our betas. And taking the derivative of this equation then allows us to solve for those betas. So when our predictors and our responses are known, we can use these least square methods to calculate what the best betas are for this particular data set. So I know that matrix algebra is a little bit complex. So to summarize, the basic idea of what we're trying to do in a general linear model is find the parameters that minimize the errors or deviations between the predicted values and the observed values, which is just like a line of best fit in the case of a simple regression. But now the parameters are more than just slopes and intercepts. They can also represent the effects of one level of a factor relative to some other level of a factor. And we can therefore code these factors as a series of binary yes or no questions about whether a particular observation belongs to a particular level in that categorical predictor. In order to interpret what our parameters mean, we need to know how our factors are being coded by the statistical package that we're using. As a reminder, we don't have to do this coding ourselves in our data file. We let the statistical package do it for us in the background when it's crunching the numbers, but we do need to understand how this contrast matrix is being put together to be able to interpret the parameters that we get out in our statistical summary. So general linear models then represent a common statistical framework that lets us assess the importance of a set of continuous and categorical predictors to some response variable. This general modeling framework then provides a lot of flexibility and encompasses the various techniques that we've talked about in the course so far, including regression, ANOVA, ANCOVA, and t-tests, as well as many more complicated combinations that we'll get into later on. This general linear model framework also provides the starting point as we expand further in subsequent videos to talk about other types of models that are based on this general linear model foundation. It's important to remember that when we use general linear models, we take our categorical predictors and describe them by a series of binary yes or no questions about whether each observation belongs to a particular level in a factor. And the parameters that we get out of a general linear model then are the parameters that minimize the squared deviations between our observed values and the fitted values. In essence, this set of parameters are the set of values that then minimize the residuals or the errors or the differences between our observed and our predicted values in our statistical model.